Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual. Today a little bit more about knot theory. Knot theory is always fun. Knot theory is always a big source of cool theorems and nice ideas and very visual, of course. But it's also a good source of a lot of questions that sound very simple and don't are really not as simple as they sound like. So they sound like they have a very simple answer, like pretty straightforward, and you can do that, whatever, on the back of the envelope. But it turns out you can't. And one of these is this crossing number additivity, which the name I made it up. That's probably not the standard name, but we will see what it means. It's really just this idea that adding crossings adds crossings. You would think that sounds true, and that's exactly why this is so deceiving. It's one of these, as I said, innocent questions which may not be as innocent as they are. So then I will eventually show you a theorem about those additivity of crossings. Okay, so one of my favorite pictures here, or two of my favorite pictures. So a knot is nothing else than a string in three space, in whatever three space you like. Here is a knotted protein on the right-hand side. On the left-hand side is maybe more the mathematical definition of a knot. But well, let's just say they live in three space, and let's say three space means R to the 3. Or you could also go do S3, doesn't really matter so much. But anyway, so they are in three space and they certainly don't knot. Okay, but you can project them, which gives you a two-dimensional shadow. We'll see it here very nicely. So here, this knot has three projections. And it's really this idea that you have some kind of light and you project it down to the plane. There's three-dimensional object, you project it down, or an object that lives in three space and you project it down to the plane. So you lose a little bit of information, but the shadows are still much easier to study. The only extra information you keep track of, you kind of keep track of which strand goes over or under, instead of just using the plane projection. You kind of keep track. And you have what is called a knot projection, a knot diagram, or a knot shadow, depends a little bit. And the number of crossings crucially depends on the projection. Here's a silly example. So the unknot is just a stupid string in R3, but if you project it, so this is a projection, and if you project it wrongly, it could, for example, wrongly, whatever that means, not very efficiently, it could, for example, look like this, which is, of course, still the unknot, but the number of crossings, as you can see, crucially depends on the projection, which is kind of the price you need to pay if you project it to two-dimensional world, because originally, of course, the knot doesn't cross at all, right? The knot itself is not crossing. It's just a string that lives in space. Okay, that's a price we pay. Maybe that's not so bad, but then a lot of questions arise about those number of crossings and what they mean and so on and so on. So here's a nice one. So the number of crossings is usually, it's very hard to compute, but it's usually very useful to just list knots by the projection with a minimal number of crossings. So the unknot has minimal number of crossings. Well, you can see it's 0, and it's the only knot with 0 crossings. And like I said again, it's a bit tricky. By crossings, I mean the minimal number running over all projections. That's a really hard number to compute in general because you kind of need to know all projections. But anyway, for some knots, you can actually do that. So the trefoil, the next one, is the only knot with 3 crossings. The figure 8 knot is the only knot with 4 crossings, 5 crossings have 2, 6 crossings have 3, and then eventually it explodes. And the table gets pretty huge, but the number of crossings is a very good way to organize knots. The problem is, and that's what I would like to stress again, this is essentially impossible to compute because, well, for a general knot, it's not enough to look at one shadow, at one projection. You need to study all of them at once. And that's an infinite number, and studying an infinite number is usually very, very hard. Okay, so that's, well, the minimum number is then called the crossing number, and that's kind of a source of a lot of problems, a lot of questions, a lot of open questions in knot theory. And here's a very, very silly one. Not silly, sorry, simple one. It sounds simple, but it's actually really hard. And it's widely open. It's one of the biggest open problems in knot theory, actually. And it's the following idea. So there is an addition on knots, which is a connected sum. It's pretty simple. If you have knot K and not L, you just cut out a little neighborhood. So we have somewhere the knot K, and you have somewhere the knot L, which is just locally here. And the only thing you do is you reorganize the strands such that K and L are now connected, right? I just reorganize those strands locally, and they get connected now, like at the bottom. And you create a new knot. You could show a lot of facts about this, so it just doesn't depend on my local picture, and it's associative, and it's commutative, and so on. But for now, I only care that this operation, which is usually called hash, don't quite know why, but it's called hash, and it's called the connected sum. So this operation actually takes two knots and produces a new knot. So you can ask the question, sounds very innocent, can ask the question whether the crossing number of K plus the crossing number of L is equally the crossing number of K hash L. That sounds very, very reasonable, right? So the crossing number of K measures how complicated K is. The crossing number of L measures how complicated L is. You kind of put them together without really touching the knot, right? This picture just stays what it is, and this picture also just stays what it is. So in some sense, the complexity should just add. And well, we don't know. It's one of the biggest questions in knot theory. And that's what I call adding crossing adds crossings, because, well, I take knot K and I take add the crossings of knot L, but I'm not sure whether this really adds crossings or whether there's now some very crazy, unimaginable simplification that you could run to make it actually simpler. That's a little bit shocking, right? It just sounds very innocent. It sounds like something someone would have proven in the past, whatever, 120 years of knot theory, roughly. But no, it's still an open problem in knot theory. But you can say something. So let me at least state a pretty cool and very recent theorem, which is a kind of strange number, 1/5(2). But anyway, a link to the paper in the description, a very nice paper. It says that the crossing number is kind of bounded, the crossing number of the hash, that's what we're interested in here in the middle, that's the crossing number of this beast here, is bounded by the crossing number and the crossing number of the sums of the crossing numbers. But it's not quite one that you can use here. The only known bound, I think that's the best bound. The only known bound, the best bound known is this 1/5(2), as in the paper in the description. And well, this is really simple. Why is this one really simple? Well, in order to check that the crossing number is at least a certain number, that's what we want. We only need to find a projection, and we just found a projection here. So whatever the crossing number here is, it can't get bigger than this one, because we take the minimum over all projections, and we just found the projections with this number of crossings, right? So the upper bound is not hard. This one is a real meat, and it's really, really hard. And this number 1/5(2) is a bit random. And that's just what it is. So the main statement here is the lower bound. And as I said, I don't know right now. Everyone, as far as I know, conjectures that this number is 1, which would give us our statement here. But the best we can do for now is 1/5(2), which is still pretty impressive. This number, 1/5(2), does not depend on K or L. So it's universal for all knots. And that's pretty cool. So what number actually could it be minimally if it's universal for all knots? Probably it's 1, right? But we can't prove that yet. Anyway. And there's some other statements related to crossing number. Here's a cool one. So whenever you have alternating knots, actually, it really works. But alternating knots form a really, really tiny family of knots. So alternating knots is when you can find a projection such that if you run around the projection, it goes under, over, under, over, under, over. Well, this was an alternating knot. Most knots are not alternating. So, but this is a general formula for any knot, and that's pretty good. Anyway, so here comes a fun fact. Paper is linked in the description. I recently learned that. I got a little bit shocked, but actually this is applicable. This is applicable in nature, and well, nature somehow knows that this is hard. And the connection is DNA actually forms knots, and a lot of the kind of real-world properties of DNA can be modeled by looking at the underlying mathematical knot. Okay, this is kind of well known for quite a while by now. It's kind of a shocking fact, that you can use mathematical knot theory to study DNA. I already had, remember, proteins on my first slide. So proteins is another example where actually the knotting structure of the molecule or whatever actually really counts. Here's another one for DNA. It makes a difference how DNA lies in space, and how do we measure how it lies in space? Well, it's a knot, and we apply methods from knot theory. And turns out that the crossing number, at least that's what explained in this paper, kind of measures or predicts the physical behavior of these DNA knots quite well, which is kind of cool. So it's kind of a good predictor. I'm not going to tell you what kind of certain properties it is. That's beyond me. It's too much physics and biology, but the paper is linked in the descriptions. So there are certain behaviors that are really good, where the crossing number is a really good predictor. And this works for, well, the prime knots, which do not arise. So the ones that do not arise under this operation, everything that arises under this operation is called a composite knot. And we just learned crossing numbers of composite knots are actually hard. Yeah? Crossing numbers of prime knots, you don't need to worry about this inequality. Prime knots are always the ones that will never show up here in the middle anyway. Okay, composite versus prime. Turns out that that's what this paper explains, that the crossing number is a good behavior for prime DNA knots. So whenever DNA forms a prime knot, it's a good behavior. And whenever it forms a composite knot, this seems to be wrong. And obviously, I just made that up. They never talk about this relatively new theorem here in knot theory. But in some sense, this theorem is about composite knots only. And the crossing number for composite knots seems to be really hard. And this somehow seems to be captured by nature, which I think is at least, may it be true or not, but it's at least a cool thought here. Anyway, so I was raffling. So what I was saying here in this video, what I'm trying to explain, is a cool kind of fact from knot theory, that a really simple question like the crossing number of composite knots turns out to be really hard. And we get this still very impressive bound with 1/5(2). The number should be, we need to improve that number to 1 to get one of these main open questions in knot theory. And then, well, turns out maybe not. This is actually really related to nature, and nature knows that, and maybe that's why nature prefers, I'm not even sure if that's true, but maybe that's why nature prefers prime knots over composite knots. I don't know, but the paper linked in the description is certainly very readable. Anyway, I hope you enjoyed the video, and I also hope to see you next time.